A couple more difficult questions now involving calculus, where we have to formulate an equation, find a maximum or minimum by making the derivative equal to 0. And both these next two questions involve volume. So the skeleton of a box is to be constructed from a piece of wire 144 centimetres in length. The box is to have a rectangular base with its length 3 times its width. Find its dimensions so that the volume is maximised. Okay, so I'm going to call that dimension there x. Okay, so the length is 3 times its width. So if that's x there and the length is 3 times its width, that means the length here must be 3 times x. So 3x. What about the height? Well, I'm going to call that h. Okay, so we've got 3x, x and h there as our dimensions. Okay, so that means that the length of this box is 3x. The width is x and the height equals h. And we know that volume is length by width by height. And as you can see, our problem at the moment is we've got x and h as our variables. So the first step, as it is with these questions, we need to get everything in terms of x. So let's work on that. Now, pointing out here that we've got to construct this out of a piece of wire 144 centimetres in length. So here's our box, and what we're going to do is get a little equation here, because we have to construct this box from 144 centimetres of wire. So that means, how many lots of 3x have we got? Well, we've got 3x there, 3x over there, 3x there, and 3x there. Okay, so we've got 12x plus, how many lots of x have we got? We've got x there, x there, x there, and x there. So we've got 4 lots of x for all the widths. How many h's we've got? We've got h there, h there, h there, and h over there. So we've got plus 4h, and all of that equals 144. So pause here if you can't see that and have a look. We've got 4 lots of 3x, 4 lots of single x, 4 lots of h, and they are the edges of the box, and they are going to make up the 144 centimetres of wire. So that means that 16x plus 4h equals 144. So that means that 4h equals 144 minus 16x. Divide through by 4, h equals 36 minus 4x. Let's revisit our dimensions then. Length equals 3x, width equals x, height equals h. Now we've now found what h is equal to. It's 36 minus 4x. So I can now replace that with 36 minus 4x. So our equation for volume then is length by width by height. It's 3x times x times 36 minus 4x equals 3x squared outside of 36 minus 4x equals 108x squared minus 12x cubed. Okay, so if we put that with the x cubed term first, that's our equation for volume. Negative 12x cubed plus 108x squared. So now we've got our equation for volume, we have to get our derivative. So to v dx equals negative 36x squared plus 216x. Need to make that equal to 0. Equals 0. Now there's a common factor here. Negative 36 can actually go out the front. Negative 36x outside of x. 36 goes into 216 6 times. So it's going to be minus, sorry, that shouldn't be x squared there. Let's rub that out. Minus 6 equals 0. Therefore, x equals 0 or 6. Now, returning to our diagram, x equals 0, so there's our width, isn't possible. We can't have a 0 value for width. So, x equals 6 is our expected maximum. We now set up a gradient table. Okay, just to save a bit of time, I've done the working there for the gradient table. I've chosen numbers either side of 6. I've substituted them into the derivative and got a positive, 0, negative. So x equals 6 gives a local maximum because we've got the pattern plus, 0, negative. Okay, before we go on to the next question, we need to go back to our original dimensions. Okay, so remember that length was 3x. Okay, actually, now what I'll do is I'll go over to here, beg your pardon, so just clear a bit of room. Might just pause while I do. Okay, x equals 6 gives us maximum volume. Therefore, the length is 3 times 6, which is 18. The width is x, x is 6. The height is 36 minus 4 times 6. That equals 36 minus 24 is 12. So they're my dimensions for maximum volume. Now, the question doesn't ask me to find maximum volume, but if it did, I would then multiply those three together. Okay, and what we'd get in that case is, let me see, 72 times 18, 1,296, and I think we're centimetres, weren't we? So cubic centimetres. There we go. So there's an example of a volume problem. Going over it again quickly. We knew that it was 3x here because the length was 3 times the width, and the width is x, and there's the height. We know that 12 lots of x plus 4 lots of x plus 4 lots of h, all the edges of the box equal 144. That enable us to generate height. Volume is length times width by height, so we're able to get our equation for volume, make the derivative equal to 0, gradient table, and then we've got our dimensions for volume. Okay, another question. A rectangular piece of cardboard measuring 40 by 15 is said to have small square pieces cut out of the corners. The sides are then folded up, forming a flat open tray. Use calculus to find the maximum possible volume of the tray. So you can imagine here that originally, before we cut the corners out, we had our dimensions of our tray being 40 and 15. What we're going to do is cut out the corners, and the corners have got a length there of x. So I'm cutting x out of each of the corners there. That would mean that that distance there now would be the original 40, okay, minus 2 lots of x. 1 lot of x from there, 1 lot of x from there. Okay, so that is now 40 minus 2x. The other dimension here is the original 15 minus the x that's cut out of there and the x that's cut out of there. So its dimension there would be 15 minus 2x. So what are the dimensions of our box? Well, when we fold up the edges there, okay, if you look at that x there and there, look at that x there that I'm circling at the moment. When we fold that up, that means the height of our box will actually be x. So we'll have x for the height of the box. The length of the box will be 40 minus 2x, and the width will be 15 minus 2x. Okay, so just take that back to the diagram there. You can see when the sides are folded up to form the box, that's what we'll get. So the volume of this box is going to be x times 15 minus 2x times 40 minus 2x. Okay, if we move the brackets there, we get x outside of 600. That's minus 30x minus another 80x is minus 110x plus 4x squared. Therefore, if I continue up here, the volume, if I remove the brackets, is 4x cubed minus 110x squared plus 600x. Now you can use calculators for a lot of this stuff, but I'm doing it without at the moment. So there's an equation for volume. Maximise volume, dv dx. So we're going to find the maximum value for x. That is, what did we have to cut out of these corners? Okay, what's that value of x to give us maximum volume? That's what we're trying to find. So dv dx equals 12x squared minus 220x plus 600. Hopefully I can squeeze that in there. Okay, we make that equal to 0. 12x squared minus 220x plus 600 equals 0. If we solve this in our calculator, we get two solutions here. X equals 10 on 3 or 15. Let's go back to our original diagram here. If we substituted 15 in for x, so let's look at this dimension here, for example. Okay, if we substituted 15 into there, what we'd get would be 15 minus 2 times 15. Okay, and that's going to give us negative 15. So 15 is not a viable answer because it will give us a negative value for width. Okay, so we can eliminate 15. Okay, therefore 10 over 3 is our viable solution. Okay, so let's look at that. We need to make up a gradient table to show that, so we'll do that right now. Just to save a bit of time, I've put two values to the left and one value to the left, one value to the right of 10 on 3, and we've got our required slope there. So x equals 10 on 3 is a local maximum because we've got the pattern plus 0 negative. Let's go back to our box here. There's the dimensions of our box. Let's write them down. We've got 40 minus 2x as our length. We've got 15 minus 2x as our width, and we've got x as our height. So we've now established that 10 on 3 gives us our maximum value. So our length will be 40 minus 2 times 10 on 3. Okay, that's going to be 40 minus 6 or that's going to be 20 on 3. Okay, which is going to be 100 on 3. I think that's going to be 33.33 centimetres. Here we've got 15 minus 2 times 10 on 3. That's going to be, let me see, it's going to be 45 on 3 minus 20 on 3. It's going to be 25 on 3. That's going to be, so let me see. Let's go here. We're going to be 15 minus 20 on 3. 8.33 centimetres. And x is 10 on 3. So that's 3.33 centimetres. Okay, so going back to our question. The dimensions here for maximum volume are going to be 33.33, 8.33 and 3.33. So I'll just put those there. Now if we wanted to work out the maximum volume here, there's two ways of doing it. We can actually put 3.33 back in the equation for volume, which is this one here. Oops, which is this one here. Okay, and find the answer using our calculator. Or, probably easier, is just to multiply those three values together. Length times width times height. Okay, so there's a couple of examples for volume. One was a box question. Okay, the other one here was a tray question. Okay, two standard sort of volume questions involving applications of calculus.